Good. Hi, I'm Kevin Pate, and this is lab number 4 for Physics 1 at Georgia Tech on oscillations. So for the introduction purpose, the reason for us working through this lab is for the physics concepts and equations that we've gone over in the lecture, and through practice problems from GPSs and the real-world applications. In this lab, we observe and examine the motion of a mass on a spring system while the spring swings an arc while also oscillating on the spring. For the principles and models involved, the energy principle is one, Newton's second law, and the momentum principle is another big one that's used. For the preview of the end results on this lab, the experimental data and model did not exactly match in numbers at certain times, but they were close, and they had the same general trajectory, and the change in total energy of the system was still zero due to a lack of work done by the ceramics. And Hooke's law is another principle that was used, and it's that the force needed to stretch and compress the string scales linearly with respect to the distance of the spring, and that's showed by this lab. When the initial conditions, the system that is set is the spring, the block of mass, and the earth or gravity force being exerted on the spring and the block. In the surroundings, there's none. We put everything in the system. And for the initial velocity, it's 0. And for the initial position, I measured it at negative 0.118 in the x direction, negative 0.634 in the y direction. And the initial mass of the block, the mass of the entire experiment is 0.402 kilograms. The equations used, there was a change in energy equation, which is the energy principle. Kinetic energy equation, potential energy of gravity, potential energy of a spring. For forces, there's the gravity in the vector form, the spring force, F net, velocity update, position update, and these are some of the variables used. The steps of the experiment, before any data that we collected could be used, it had to be collected in the first place. The tracker, which is used to track the motion of an object, such as the one we did. And I had to create a CSV with the X and Y data collected from the tracker through Excel. And I had to input the data from the experiment into a below script code to create a simulation and compare that to the physical experiment. This was the video that we all used, and this is the tracker data that came from it. This is the code for the glow script. And on this left side was the initial conditions that was set, and I was getting the energy, the total energy, the spin potential energy, and the gravitational potential energy, along with the kinetic energy. And I added these up to get the total energy at the beginning. And then for the while loop, I set our conditions for the current step to the initial conditions. And then I got the gravity force, the spring force, F net was the addition of those. And I set the other conditions that be measured throughout. The results, these are the graphs that came from it. There's one for the X, here's one for the Y. And here's the change in energy versus the change in time. And as you can see, it still hovers on 0 for the, it's still they have opposite trajectories. For the modeling versus experiment, the numbers varied slightly, the exact values at the related times. They follow the same paths and trajectories, and they support the same conclusions, which we'll get to at the end. The computer model is more consistent, particularly in the parts where the oscillating and swinging object changes its direction, which is not shocking. And this is likely due to the lack of human error that could be involved in the computer model. What does it mean? The energy principle is satisfied. There is not a loss of energy, and there is no change in total energy within the system due to a lack of outside work from the surroundings, which is expected. And so this means the kinetic energy change and the potential energy change equals 0. The estimated period of oscillations for the second question predicted through the difference in max and mins of the model. For X, I got 1.6 seconds. For Y, I got 1.52 seconds. Possible sources of error throughout this lab. I could have made a mistake in the tracker analysis when I was trying to trace the center of mass. I could have just been not on the center of mass and misclicked. I could have mistimed the step. And I could have made the error rounding throughout the initial conditions and calculations involved in this lab. And with the conclusion, the energy principle is satisfied through the experiment and computational model. Newton's second law holds, and the object continues to oscillate and swing at a predicted speed by due to lack of interaction with the surroundings, which is expected. And the computational model and the data from the real-life experiment vary slightly in values, however, they follow the same paths and support the same conclusions and principles, which is expected. Okay.